So my name is Sarah Walker. Welcome to this session, which is a joint event between HIACT, Hydrogen Integration for Accelerated Energy Transitions, and the UK Carbon Capture and Storage Research Centre. HIACT is a hub that is funded by the UKRI and is looking at ways in which hydrogen can be integrated into our wider energy system and where hydrogen can bring most value to the energy transition. We are a consortium of 11 different universities. We started in June of last year, so we've not been going for very long, but colleagues in this network have been working on systems integration for quite some time, and it's lovely to have an opportunity to talk about hydrogen and to work collaboratively with other networks like UKCCS. So I'll hand over to Richard to give a hello as well.
Thank you, Sarah. My name is Professor Richard Marsh. I'm a Professor of Energy Systems at Cardiff University, and I am one of the investigators on the UKCCSRC. Our current incarnation is that we exist as a UKRI Network Plus, but we have existed under other funding sources in the past. We've been around for a little longer than that. Now, I'm probably going to get told off if I get it wrong, so I'm going to say about 10 years. We've existed in various forms with quite a significant number of academic and industrial partners as well. Now, if you've not experienced any of our events before, you might be wondering what our specific interest in hydrogen is, if the remit of the centre is in carbon capture. So obviously, our interest comes from the perspective of blue hydrogen and how that might work into a net zero society, both from the perspective of as an energy vector and as a source of energy, but also for heating decarbonisation and how that would work across things like industrial clusters and larger scale deployment. So this is a really great opportunity for us to work with HIACT and see where there is some excellent crossover. And that is why we've got speakers from various backgrounds today who are going to give their perspective on what our future looks like in terms of hydrogen. And we'll certainly be, from the UKCCSRC perspective, interested in that angle in terms of blue.
Hi, everyone. My name is Ben Wetenhall. So I'm a lecturer in engineering at Newcastle University. And also I'm a co-investigator like Richard on the UKCCSRC. Right, so I was asked to talk about spatial considerations of hydrogen and carbon dioxide pipelines. And my interpretation of that is basically, where do you put your pipeline? How do you route your pipeline? So I'm going to talk about a few things. So I'm going to talk in general a little bit about how you choose a pipeline route. So how do you select your pipeline route? So I'm going to talk about some of the major factors that you need to think about. And then I'm going to give some examples of some of our work that we've done that goes into a pipeline route selection. So I'm going to talk a little bit about failure frequency of pipelines. I'm going to talk a bit about risk and consequence, try and prevent things going wrong. And then I'm going to talk about something that's been hinted about already, about interfaces between infrastructure. How do we model those and how do we include them? Ooh. And lastly, I'm going to end with what I think are the challenges and the opportunities in this area. Okay. So how do we choose a pipeline route? So what are the major factors? Well, these are some of the major factors that go into overall pipeline system design. So you need to know where your supply and demand points are. So you need to know where your hydrogen is being produced. Sorry, just moving this out a moment. Where hydrogen is being produced, where your CO2 is being produced, where your hydrogen is required, where your CO2 store is, for example. And you've got to include build-up points as well. So maybe you're collecting hydrogen en route on the way. Maybe you need to store it on the way. Maybe you need to store your CO2 partly along the way. Another major important thing is what the fluid is and your fluid properties. So maybe you're dealing with 100% pure hydrogen. Maybe you're dealing with 100% pure CO2. A lot of the times you're not. And this has a major effect on the fluid properties. You're dealing with different phases. So you may be in the gaseous phase, you may be in the liquid phase, and different conditions as well. So maybe you've got different flow rates, different pressures, different temperatures. When you're making a route, you need to make sure you comply with all your legal frameworks. So you need to make sure you build to code and to standard, so everything's safe and legal. And when you're building a pipeline, obviously the quickest way to build a pipeline is just in a straight line. However, things aren't always so easy. You've got to really consider what's on the route, the topography, access. So you've got to think about things like if you've got river crossings, if you can jump in with energy corridors, if you've got mountain passes, or if you're passing close to heavily populated areas, you've got to consider all those things in a very detailed way. Also have to consider the environmental impact on the way, which depends a lot where you're going. So it's very case specific, but you have to consider the environmental impact of building a pipeline. You have to make sure you've got you've considered integrity and also pipeline protection as well. So maybe you need some kind of coating of the pipeline. You maybe need to bury your pipeline, and also how you're going to manage risk as well. And last but not least, economics. So a lot of things go into the cost of this. The major cost of a pipeline is generally the capital cost is generally mostly made up of the pipeline material and the installation. However, you've also got to include your facilities along the way, so things like compressor or pumps. The material of the pipe makes a difference. So if you want a higher grade pipe, it's more expensive. If you want to pass close to something like a heavily populated area, you've got to make your pipeline even safer. So location factors into your cost. And as part of your route, you might have to change your route to deal with things like crossings, mountain passes, and this can also affect your facilities as well. So maybe you need more compressor stations or more pumps, things like that. So case by case, but these are a lot of the major points you consider when you're designing a pipeline system, but not everything, but I don't have time to talk about everything. So I'm going to talk about some examples of what you need to include in this, the kind of models. So my first example, I'm going to talk about failure frequency. So I'm going to talk about carbon dioxide pipelines because that's what I've been working on mostly. So first of all, why do we need to consider failure frequency for carbon dioxide pipelines? Well, carbon dioxide is a hazardous substance and it's toxic in high concentrations and can also be an asphyxiant. And if in the unlikely event that there was an accidental release from a pipeline, you could have quite a large inventory released, and if people were there, it could cause them harm. In the UK, the pipelines could be routed quite close to densely populated areas, just because we are quite a densely populated country. And we need to understand the risk. So to get the risk, we need to know how likely we are to get failure, which is where the failure frequency comes in. And we also need to know the consequence of failure as well. So because CO2 is quite different to natural gas. So natural gas is explosive, it's flammable. CO2 isn't explosive or flammable. The risk considerations are quite different for CO2 pipelines when compared to natural gas or even hydrogen pipelines. So you need to consider them quite differently. And you're going to need a QRA, a quantitative risk assessment approach. So as part of your QRA, you're going to need to know your failure frequency. So we focused on looking at what's called third-party failure frequency. So third-party failure frequency is the most common for oil and gas pipelines in the UK. What does third-party mean? Well, that means that something other than the operator comes and hits your pipeline. So it could be a farmer digging in a field, for example. So something other than the operator is the third party, and this is quite a common method of failure for pipelines. Now, there are failure frequency models that exist in industry, and there's no reason why these can't be used for carbon dioxide or hydrogen pipelines too. They're just pipelines, right? Pipelines are pipeline. So how do these models work? So they use semi-empirical failure equations for the failure, and they use historical damage as well. So they use data about previous accidents as well. Now, what about CO2 pipelines? The thing about CO2 pipelines is most efficient to transport in what's called the dense phase, so a dense liquid. And this typically means that you're going to need high wall thickness pipe. So you're going to need quite thick pipe. The thing is, because the semi-empirical, the models that have gone into producing these failure frequency models, this is going to push them out of their applicability for CO2 pipelines just because CO2 pipelines are so thick. So it could push them out of the range of these current failure frequency models. Also, current UK fault databases do not include data for dense phase CO2 pipelines. Why? Because we don't have any. Okay, so there hasn't been any incidents in the UK, so we don't have the data about the failure of dense phase pipelines, and there's limited data for hydrogen as well. So what we did is we created a new failure frequency model suitable for dense phase carbon dioxide pipelines, and that can also be readily updated to the latest fault database as well. And that's not out yet, but hopefully it should be out later this year. So keep an eye out for that if you're interested. Okay, I want to talk about another example. So for risk, you not only need how likely you are to fail, your failure frequency, you also need to know the consequence of failure. So CO2, like I was saying before, is a hazard if it's in high enough concentrations. It's also denser than air and it's odorless, which means if you get a release of CO2, it will fall back down to the earth because it's denser than air and drift along in the wind. So it could drift along in the wind as a cloud of CO2, and it can drift past buildings when it's carried by the wind. So one of our projects was looking at how CO2 could pass from outside into the building. So how much risk exposure would there be to people in buildings? So we need to be able to calculate CO2 concentrations in the buildings as part of a QRA. Because so if you see this plot on the right, so a cloud of CO2 can pass the building. So we've got a concentration against time. So as the blue line is the CO2 concentration outside the building. And if that was constant outside of the building, eventually the building would reach the same rate, reach the same concentration as what's outside the building, if it was there for long enough. In reality, the CO2 cloud is going to pass the building, but still some CO2 is going to go from outside to inside, and we need to know how much. So my blue line here is how much is outside the building, and my red line is how much passes into the building from outside. So you can work out the consequences. So we created two kinds of models that can tell you this. We created an analytical model and a CFD infiltration model, and you can use those to predict the effect of CO2 exposure on humans inside buildings. I'll put the link on the slide as well if you're interested in the publication. How does the model work? Well, I'm just going to briefly go through it. So the model, if you want to see, it's described in the paper, but basically it considers wind and buoyancy driven airflow. So if the wind is incident on a building, it's going to push the CO2 into the building if the CO2 is sitting outside the building. Also, there's going to be flow inside the building because of buoyancy. So the CO2 is quite cold in general, and that will affect the flow inside the building. So depending on the pressures and the temperatures, that will affect the flow. So we've considered that and the wind. And then the model produces just a single concentration inside the building. And one thing that's important, so we needed it to be computationally efficient, because you can imagine if you've got quite a long pipeline route, you're going to have to perform risk assessments in quite a large area. You need it to be computationally efficient. And I think this is kind of a theme for a lot of this geospatial considerations. So because you're dealing with quite large areas, you need the models to be very computationally efficient. Okay, another example I want to talk about is interlinking between models and interlinking between different parts in the system. So when you design a system, you need to design your system to be able to work together with other systems. So what do I mean by that? So in blue hydrogen production, you've got your carbon capture and your hydrogen production, and they need to work together in harmony. For green hydrogen, that has to work in harmony with renewable energy to produce hydrogen. So different systems have to work together, and this is going to propagate outwards as well into full systems, and it can be quite complicated. So one of the examples we looked at in carbon capture and storage is the link between offshore infrastructure and pipeline infrastructure. So we looked at how uncertainty in CCS store properties, so things like pressure, temperature, depth, and sorry, clicking on itself. My slides are misbehaving, sorry. We looked at how pressure, temperature, depth, and permeability, for example, can affect store properties, because maybe you think you know what your store is going to be like, but in reality, it might be a little bit different or a lot different. You're just doing it from your best guess. Anyway, and these uncertainties can affect your transportation infrastructure, because they can lead to variations in injectivity and permeability, which means that maybe you can't have the CO2 flow that you were anticipating, which in turn affects your transportation infrastructure. Also, a lot of the time at your wellhead, the conditions that you're operating at, the pressure and temperature conditions, means that you're quite close to your equilibrium line, and also the maximum limit on velocities. And that can constrain your operating envelope as well. So this can limit the ability of your storage site infrastructure to handle these variations coming into the store. And if the store's affected like that, if the flow of CO2 is affected like that, then that is going to affect your design of your pipeline. Oh, sorry, I don't know why it's flicking on. It's doing it itself. My internet connection is okay, but my slides are misbehaving. So yeah, that can affect your design of pipeline. You need to include that in your design of the pipeline. So variations in store properties basically affect the level of injection that you can be and how flexible you can be. And you need to design these into your transportation system so that it can handle the CO2 flow at different conditions and probably be more flexible than you were designing to. Okay, another example of what I've called interlinking. So you can use a pipeline to temporarily store your fluid in. It's called line packing. So during line packing, the flow out of the pipeline is stopped by closing or throttling a valve downstream, while still allowing your fluid to flow into the pipeline. So as a result, the fluid in the pipeline is compressed and the pipeline can be used as temporary storage. It's called line packing. And the amount of this line packing is limited by the maximum operating pressure of the pipeline as well, which you can't exceed. So line packing is used a lot in the natural gas industry, and you can imagine it allows your system to be quite flexible. So it's good to have a nice amount of line packing time. And the level of flexibility for the pipeline to access short-term storage is very useful when you're looking at systems design. So whether it's CCUS or hydrogen, the amount of fluid that you can temporarily store in pipelines is useful for dealing with things. If you need to switch things off downline or upstream, you can use the pipeline as a temporary store. So in our work, we found the available line packing time for carbon dioxide pipelines. We found relations in terms of the pipeline geometry. So how thick the pipeline wall thickness is, how big the actual pipeline is, both in terms of the diameter and length, how much mass flow rate you've got coming in, and the conditions in the pipeline, the pressure and the temperature. So we've published relations between these variables, and the relations allow you to estimate the line packing capability of carbon dioxide pipelines. You could do the same for hydrogen in terms of your pipeline design and operation as well. And for typical kind of CO2 pipelines, dense phase CO2 pipelines for carbon capture and storage schemes. So typically pipelines can act as a store for your CO2 for about 10 hours at a time. That's what we found. So like I was saying before, so this line packing time, you can use it as short-term storage in the network, so full systems. And you should think about that when you're designing your network as well, because it can really help how your system works together, including when you're reusing infrastructure as well. Okay, so lastly, I just wanted to talk quickly about challenges and opportunities in the area. So when you look at your pipeline route, so when you look at your spatial considerations for hydrogen or CO2 pipelines, whatever, it's essential so that you get an optimized design, so that you get a safe design, that you minimize environmental impact and enhance overall efficiency, and you make the best economic case that you can. You need to think about integrated modeling because these systems will work together and the effects will propagate outwards into the full system. So you need an integrated approach that you need to consider both hydrogen production and transportation, as well as carbon capture and storage in a spatial context. Consider the whole system and how systems work together. So, for instance, if you've got green hydrogen production, you also need to consider integration with renewable energy You need to consider what's going to be available in terms of infrastructure, for example, and water resources, for example. So lots of different things to think about, but you need to think about how everything can work together to get the best design. When you're designing quite a large amount of infrastructure that's complex, you generally need your models to be quite computationally efficient, because you can imagine you can't wait forever for your design. They need to be quite quick. I had to put AI in because it's very cool. But anyway, no, what I was thinking about for this, so when you're routing a pipeline, a lot of it is looking traditionally at maps and looking, so where's my river crossings, where's my mountains, how is it best to avoid them, is it better to go further from densely populated areas? So a lot of data goes in to making these routes and a lot of detailed work, and there probably is potential for using AI there as some kind of quicker and smarter way of doing pipeline routing. So I definitely think that's an opportunity for the future. Risk, well, risk is generally inferred from historical data. The thing is, there are no dense phase CO2 pipelines in the UK running, and there's very limited hydrogen pipelines. So getting that risk is quite difficult as well. So you need to think about how that's best done. And that's everything for me. Thank you.
Thanks very much, Ben. So we'll now move on to our third speaker today, and that's Dr. Tong Zhang. Tong is from Cardiff University and works on HIACT, the Hub on Hydrogen Integration for Accelerated Energy Transitions. Tong, over to you.
Yeah, thank you very much, Sarah. Let me share my screen now. Okay, I'm just gonna turn down my camera to make sure the network is okay. Okay. So good afternoon, everyone. Thanks for attending this webinar. I'm Tong Zhang from Cardiff University, and today I'm gonna give a short talk about the spatial considerations in energy system models with hydrogen integration. A little bit background of this presentation. Last year, we've conducted a literature review looking into the energy system models that considered the hydrogen integration. We examined publications between the year 2012 to 2022, and we summarized some of the key features in the energy system modeling methods that had considered hydrogen integration. And obviously, spatial considerations is one of the key features. So this is why I'm here today, I think. So outline for this presentation, I'm not really sure how many audience come from the field of energy system models, so I'm gonna give a little bit context. Then there will be introduction about energy system models and spatial considerations. So why we need energy system models to study hydrogen? This can be thought about in two parts. From the technical aspect, hydrogen itself interacts with other sectors through different hydrogen technologies. For example, there are water electrolyzers connecting electricity and hydrogen. There is also different hydrogen-powered vehicles and trains, maritime applications, and also applications in aviation to connect hydrogen with the transport sector. So if we are thinking about hydrogen, we naturally come to think about what is hydrogen doing in other sectors as well. And from political or strategy aspect, there is something called a whole system approach to developing hydrogen technologies. The UK hydrogen strategy released in 2021, you can see that you can find that there is a hydrogen economy 2020 roadmap in the file, and it shows the gradual scale up of hydrogen economy with power sectors, industry, heating as well. And further, in last December, a decision on the framework for the future system operated centralized strategy network plan, this is a long name, has also put the hydrogen production into the consideration of strategic planning, and the hydrogen transportation and storage will also be considered after 2026. So therefore, when we are thinking about hydrogen, when one needs to study about hydrogen, it's quite necessary to put hydrogen into within the bigger picture, which is the whole energy system. So something about energy system models. When we try to study energy system model or the hydrogen's role in energy system models, we need some tools to give us some insights, some understanding, do some calculations, have some analysis, and that is what energy system models are here for. And energy system models, in my understanding, there are different types of mathematical models that can describe the operation or the physical constraints, technical limitations of each component inside the energy systems, and also reflect the interactions between different sectors. So the elements or the components can include energy sources, conversion, storage facilities, transportation and distribution networks, energy consumers, etc. However, there are also different input and output. However, these can be very different according to the different research questions or the study objects of these energy system models. But the most popular ones include energy supply and demand, technical, economic, environmental factors of performance of technologies, and also social environmental implications, as well as development plan, system design, operation schedule, etc. Sometimes, for example, energy supply or the capacity of a hydrogen electrolyzer plant, they can be something something already known as a data input in some of the models, and sometimes they are something we don't know and we want to figure it out in the energy system models. These all depends on the research questions we are looking into. So about the questions, there are a lot of questions out there. I think we can roughly classify them as two types. One is planning or designing, that is to plan how the infrastructure would be constructed or expanded, or investment decision making. And another one is to do the evaluation. It's more about we already know the design of the energy system and we want to know how this energy system or different energy technologies, for example, hydrogen technologies, will operate in this kind of system model setups. And then we can do further analysis based on these results. And what kind of answers are corresponding to these two types of questions? For planning, of course, we can know the optimal design. For example, we can have the most economic plan to deploy different energy assets, and also doing the best investment strategy decision making. And for evaluation, there will be an optimal schedule or dispatch of different different components inside the energy system, and therefore we can know the revenue, the profit, the cost, and the technical performance or environmental performance of the whole system or individual components. And these all are the solutions coming from energy models and can be used to support further analysis and inform decision makers. And finally, down to the spatial considerations. Spatial considerations, from my understanding, is more like something that has spatial or geographical features. And this can actually be found anywhere in the energy system models. It can be reflected by objective functions, input data, constraint, and output, etc. So about energy system models that considered the hydrogen integration. This is some modeling landscapes that we've got from the literature review. This is a summary of geographical coverage in the reviewed publications, and you can see there are worldwide or Europe international energy systems, and there are also national or regional case studies coming from different countries, as the hydrogen economy development stage in different countries, as well as the national strategy are different. Of course, the input, the model formulation, and all of stuff might be different due to the because of the different geographical coverage. And another thing is that in our literature review, we are investigating the larger scale energy system models. And in reality, there are different scales. There might be national, regional, international ones. There may also be local level or community level energy system models. And different scales usually require different spatial features in the input data and model formulation. And another thing is that in the energy system models, usually there might be different sectors and hydrogen technologies that have been included in the models, and different hydrogen technologies will lead to different spatial considerations in the model formulations. For example, there are quite many publications that specifically investigated the role of electrolyzers in the integrated electricity and hydrogen system. So you can see that some of the publications, they only covered hydrogen production technology, and for sectors, they only cover hydrogen and electricity, or sometimes plus natural gas. But for example, no heating sector is involved. So therefore, it is quite hard to give a very generalized conclusion that what kind of spatial considerations are there in all the energy system models. And it might be easier to say that different spatial considerations are included by different hydrogen technologies. So what I'm going to do here is to walk you through the model of different hydrogen technologies and how they are modeled in the energy system models and the spatial features inside the models. So the first of all is hydrogen production technologies. The most popular topic, or the most popular technology here, is the water electrolysis. Electrolyzers have been included almost by all types of the energy system model-based studies. You can find it in smaller scale energy system, bigger scale like aggregated national scale energy systems as well, and their operation details can be modeled when you are looking at hourly or daily operation, and sometimes they are just represented by hydrogen supply profiles in some aggregated energy system models. For the spatial considerations, I will talk about from two parts. One is when the model are used for planning or designing purpose, and another one is used for evaluation or looking into the operation of the energy system model. So in spatial considerations in planning, the location and the capacity of electrolyzers will be influenced by the access to water resources and electricity supply, and also distance to the hydrogen transportation or distribution network, etc. There are a lot of factors to consider. All of these can be reflected in the constraint in optimization models, or it can be regarded as some sort of data input and later on using in the multi-criteria decision making, so that you can find the best location to build electrolyzer plants. And for the evaluation here, for evaluation and operation model, usually we already we know usually we regard the layout and the capacity, the layout of the energy network and the capacity of different component energy assets. They are already known. So what we will pay more attention to is the distribution and pattern of hydrogen demand, renewable energy capacity and price. For example, in Scotland, you have there are more wind farms. So if you are looking at wind-powered electrolyzers, there will definitely be more productions out there. And also another thing is about the layout of power grid and pipeline network. For electrolyzers, you need power supply. It's either from renewable energy generation side or from the power grid. And also you need some way to transport hydrogen. And one way to do that is pipeline network. So you need pipeline network. So you also need to consider how the electrolyzers and network will be working in coordination. And for steam mason reforming, SMR has also been considered by all sorts of energy system models, but usually they are only represented as input data like hydrogen supply profiles, patterns, or data. The detailed operation model of SMR is now considered by most of the energy system models. And for spatial considerations in planning, another thing to consider, special thing considered for SMR is the access to natural gas resources and natural gas resources. The spatial considerations in evaluation, they are mostly similar as electrolyzers. And for other hydrogen production technologies, we know there are biomass gasification, also thermal reforming, etc. But these technologies, they are relatively higher, relatively more expensive and smaller in capacity so far. So usually they are not much detailed modeling about these technologies, and there are not much spatial features to consider for this technology. And for hydrogen transportation technologies, this is a figure I screenshot from the report from International Renewable Energy Agency, and you can see that the hydrogen transport cost is different, varies by distance and volume, and this is also something will impacting the selection of hydrogen transportation tools during energy system model. And for road hydrogen transportation, sometimes there are very detailed modeling about road transportation tools. For example, tube trailers, tank trucks. When you are looking into a smaller scale energy system modeling, there are actually a mathematical constraint to represent how each car's going around, how each truck's going around. And in some other like larger scale energy system models and also hydrogen supply chain optimization models, they are sometimes represented as the hydrogen or the energy flow between different nodes and with less details. And for the spatial considerations in planning and evaluation is they are usually about the distance to the hydrogen production site, refilling stations, and hydrogen end users, as well as the road rules and traffic conditions. One way to, and since the road hydrogen transportation is connecting the hydrogen production and end use, sometimes the distribution of hydrogen demand or supply may vary in different area. So that is also something to consider when you try to get an optimal plan to dispatch different hydrogen transportation tools. And for pipeline, I think Ben and Zhang have already given enough information. So pipeline, we have witnessed a surging number of publications regarding the pipeline network within the picture of electricity, gas, and hydrogen networks in the last few years. And for spatial considerations, it's usually something to do with the geographical distribution of hydrogen production, demand, and configuration technical requirements of existing natural gas pipeline network. There are multiple planning related models that consider different hydrogen injection rate over the years in order to reflect the hydrogen injection ratio limit requirement. And for the considerations in evaluation or operation models, this same things happen here. So because the hydrogen injection points, they distributed across the whole energy systems, and also the injection is changing all the time. It's changing all the time for the green hydrogen, especially for the green hydrogen, usually for the green hydrogen production site, because it's related to the wind power output or PV output or etc. So the hydrogen injection ratio may vary with time, and therefore leads to an uneven distribution of hydrogen blend ratio or gas composition. And you can and when there are more green hydrogen injected into the energy system, there will be a stronger coupling between the electricity network, electricity power grid, and gas network and hydrogen system. So the spatial distribution of hydrogen injection points and the changing pattern of hydrogen supply and demand should definitely be something to be considered in the models. And for other hydrogen transportation technologies that are mainly, another thing is shipping, and it's more to be found, it's usually to be found in international trading. And hydrogen storage technologies, I need to speed up a little bit. So tanks and vessels, they are very commonly seen. And one thing to think about is to connect the hydrogen production and consumption. For underground hydrogen storage facilities, it's usually very related to the geological condition of the potential UHS sites. And no matter it's for planning and evaluation, the technical requirements or the capacity, the cushion gas requirement, etc., of underground hydrogen storage it's very spatially featured, because it is different in each place, and that is something to be considered in the energy system models. And finally, hydrogen consumption in different sectors. So the hydrogen economy development is facing a chicken and egg dilemma, and the industry hope to tackle this with the coordinated development of both hydrogen supply and demand. And hydrogen demand comes from industry, transport, heating, and electricity. So for industry, the hydrogen demand is usually represented as hydrogen demand profiles, like an input data. And other things to consider about the hydrogen consumption during the modeling is the distance to the hydrogen production and demand. Sorry, not distance. The level of hydrogen production and demand. And another thing to think about is the competing technologies. For example, the electric vehicles obviously outnumber the hydrogen-powered road transport. And when you are thinking about doing planning for hydrogen on-road transport, you must have to consider how much transport demand is satisfied by EV fleets. And this happens the same for heating. For heating sector, you have heat pumps and you have gas boilers. So it's you definitely need to consider how much is the market demand for hydrogen from the heating sector. Lastly, I want to talk about a little bit about geographical information system. There are several publications that has been completed based on the geographical information system. It's working as a source of data input to help the decision making in the optimal planning models. For example, you use GIS to give information about the local about the hydrogen demand, the renewable energy resources, and the distance to different hydrogen infrastructure like storage and pipelines, and all of this can be fed into the optimization models or used in multi-criteria decision making later. So the researchers can find the most suitable locations to build new plants or new infrastructure. So challenges and trends. There are definitely uncertainty issue in energy systems and hydrogen economy development. This coming from like short-term uncertainty like demand and supply. It also comes from the uncertainty lying in the hydrogen technology, policy, market penetration level, etc. These uncertainty factors will be different in different areas in different countries. So definitely a challenge. And secondly, needs to integrate more spatial considerations as there will be more types of hydrogen technologies in the picture. And also when thinking about the whole energy system, there will also be other spatial considerations coming from other non-hydrogen related technologies. And third, managing the modeling complexity, just as Ben mentioned, we need to manage, we hope to make sure the model is computationally efficient while still keeping enough details to get an accurate result. So conclusion, yes, definitely when doing energy system modeling, we need to incorporate spatial considerations, and different spatial considerations are included in the models that tackle different research questions and cover different hydrogen technologies, consider different sectors. So there will be different emphasis when one is doing energy system modeling with hydrogen technologies. And third, GIS has been and will be useful in energy system studies considering hydrogen integration. So basically, that's all from my side. Thank you very much.